Alright, so what I'm doing here is to write a quick and dirty program to do resolution. This is the kind of mess that we dealt with earlier today in class. So this is a program that I'm just writing from scratch. I mean, I do understand the mechanism of resolution, and but other than that, the program is not pre-done for sure. All right, so we are going to switch to the programming mode here. So I'm gonna write the program in just plain C, not even C++, because I'm for the most part a C programmer and not a C++ programmer. So I call the program resolve.c, and we'll probably include the usual stuff. Standard io.h is back in the older days, people output stuff to the standard output, and the get stuff from the standard input. And then the first thing I need to do is to define the number of variables. So numvar is a macro. Most people don't use macro these days anymore. Um, but since I'm an old timer, this is the way I used to do things. So I'm just gonna use macro instead of a const int to define the number of variables. And then what we'll do is we'll define a type for this sort of stuff. So we can use a type dev. I mean, that would work too. So type dev. There we go. And type definition is kind of making a macro or a equivalent name for a type that we normally use. So what we can do here, oh, okay, I'm also going to pound include standard integer.h. So this way I have access to integer types, of a fixed width. So in this case, I need int 8 underscore t, which is an 8-bit integer. And the type I'm defining, we'll call that um, disjunction element. Okay, so this, I don't know. I typically just call it DE. In here, we can call it WFF. Okay, there we go. So we'll call it WFF, because within the propositional logic system, a disjunction, that only consists of variables and the negation of variables is well formed within the specialized system here. So we'll just call it WFF, and it has 5 elements in it. Numvar is going to be the number of elements in this. So now we have a type already defined. We just need a way to initialize and get things started here. Um, let's see. So the next thing I want to do is to have an initialization that is based on um, hmm, I'm considering whether I want to kind of do this um, in a way where I can input stuff and just have it parse and create the um, expressions based on standard input, or whether I want to hard code it. So I haven't really quite decided yet. But I think it is probably a better idea to have the thing to do the initialization. So we'll go ahead and do that. So we'll say init wff, and we'll give it a pointer to a wff. So wff, this is the pointer to the structure that we are, or the array that we are initializing. And then we'll also give it a string, const char str, which is the text representation of the wff. All right, so what we're going to do here is to scan it, um, and what I want to do is to scan from the okay, I'm going to have it to return a const char pointer to, because this way I can parse and basically just return the last point of parsing, and then the next one can start with that. So it just makes it kind of more quote unquote stackable. And okay, I'm just looking at my cable here. It's a little constraining. All right, so what we'll do is we'll scan for the open paren. So we'll say if str points to an open paren, then we'll do the processing here. And the processing is, oh, I need to keep track of the return pointer. Okay, so we'll say this is const char next, and we'll return next here. All right, and the else statement, so the else is corresponding to, I'm not seeing what I really should be seeing or what I'm expecting to see. So it's an error condition. So in that case, the first thing I want to print is expecting open paren, and that's it. Okay, it's just an error message, and I will initialize next to a null pointer here because I need a way to return a value that is representing that we encounter error. Do not even bother to proceed any further. All right, so in here we'll say next is initialized to str, which is at the beginning of the string, and then from here on we'll just refer to next as the pointer. So once we recognize the open paren, then we'll increment next here. And then what we'll do is we'll stay in the loop to look for variables or the negation of variables until we see the close parenthesis symbol. So we'll say while next does not equal to the close paren character, do the following. And oh, I need to initialize everything in PW to zeros first because by default nothing is found. So we'll go ahead and do that. I need an integer or some kind of index variable. Unsigned int is fine. And then we have a for loop. I is starting from 0. I is less than numVar plus I. And what we want to do here is to say PW. I'm not sure about the syntax because we'll see. Because I'm not sure whether this is gonna work or not. We'll find out. That's initialized to 0. And because this I is it only has use up to here, so we'll put a local scope around the entire thing and then reformat things accordingly like so. And now we can go back and right, so I was trying to make sure that this thing at least compile first. So this is going to be a pretty long session because I'm just talking and programming at the same time, so you can definitely feel comfortable to kind of fast forward and just kind of spot check, where the program is at any point. All right, so GCC-C because I just need to compile and look for compile time errors at this point. And okay, so no errors. Okay, so I got the syntax right. All right. Okay, so next thing we need to do is to simply go through this loop here. So there are two characters that I can expect to see. One is a variable character, and then the other one is the negation operator. So we'll say if next equals to the negation operator, which is the exclamation point, then we'll remember that we have a negation operator, and then the next one has to be a variable. So we'll go ahead and say, so if I don't want to put in a lot of error checking thing because I'm fairly sure that I got the error checking stuff done already or the input is valid. So what I can do now is simply to specify int 8 underscore t. This particular local variable is to remember whether we are seeing the variable unnegated or negated. So we'll say, okay, I need to come up with a good name for the variable so that the program is more or less self-documented. So we'll say, I'm thinking about polarity, but I am I suppose we can say asserted, okay, instead of negated, right? So asserted is initialized to be true, and then what we can do here is to say, oh, by the way, after we parse or recognize the exclamation point, we need to move ahead by one character. So the next one has got to be PQRST, so I am making an assumption. So if I don't want to do something like that, I can do a const char first var equals to p. So this way, I'm just turning uh, the the character representing the first variable to be p, and that can be now reprogrammed to something else later on. All right, so this is without error checking. I'll do something like this. I'm just simply using whatever next is pointing to, subtract. Okay, I cannot remember the name of the variable already. First var. Okay, so minus first var equals to asserted. And I also forgot to negate asserted here because um, if I see an exclamation point, then I'm looking for the negative version of the variable, so I have to put a -1 to the position that is corresponding to the variable that I am processing at this point. All right, so and then after this, so I'm making an assumption that I am in fact reading PQRST here. So next has to be incremented again to move on to the next thing. So by the time I exit the loop, next should be pointing to the close parenthesis character, and at that point I can do next plus plus 2 because I want to skip over that one, and then the return value is simply next here. So this way I can use a single string as the input of this program and just repeatedly call this particular subroutine until it returns a null value because there's nothing left to process. This one does not skip spaces, so everything has to be in a pretty specific format. So now what I can do here is to supply argc and also const char star star argv. This is how we pass a command line argument to a C program. Argc is the counter, which means how many things is on the command line that is supposed to pass to main. And then argv is an array of strings. The first one being the command itself, which is usually useless and tossed away. And then the second one, which is at index 1, is the first actual argument that we pass to the program. So at this point, we can say if argc is greater than 1, then we actually got some work to do. Otherwise, we'll go ahead and just say printf um, supply a CNF as an argument. So I'm just printing, basically an error message to say, I'm expecting to see a string here, but nothing is passed to me. All right, so in the case that I do have at least one argument, the first argument is going to be the string that I want to process. So this is where things can get also a little bit tricky because I don't really know ahead of time the number of disjunctive elements. So that means I probably should not be using a fixed array to do this. Now I can use a fixed array because in this case, um, it is the total number of CNFs that can possibly be used in this system is 3 to the power of 5. Okay, so it's definitely a finite number. It's not large enough that the compiler cannot allocate something that big to begin with. So we can do it that way, but to do dynamic memory allocation is probably a little bit more reasonable. So this is C++, or this is actually plain C, and it's not JavaScript. JavaScript is easy because if you have the array type, there's actually a push and a pop that allows you to append to the end of the array really, really easily. Um, but this is C++, so there's no built-in data structure that I can assume. So I'm thinking maybe I'll just go ahead and implement my own data structure here. So we'll go ahead and implement a structure, and we'll just call this a WFF node. And inside we have a WFF as um, the first member, and then we have a pointer to point to the next one. So struct WFF node next. So I'm just creating a linked list, right now, on the fly to kind of keep track of all the WFFs, that I have discovered. And once I have a data structure like this, I have to implement what we call uh, there's a name for this, abstract data type. That's right. So abstract data type requires to access a structure like this, using only subroutines that are supposed to work with this. So we can go ahead and start with stuff, right? Um, let's see. We need to extend the linked list. Okay, so we'll say um, void init linked list, and the parameter that is passed here is going to be a struct double pointer from the beginning of the linked list. So this is the pointer to the head of the linked list, and that usually means p head needs to be initialized to a null, because that means we have an empty linked list. And then the next thing is to append to the linked list. So we have append to the linked list, and we are giving a pointer to a structure. Okay, so this is a WFF structure or WFF node structure. And also we have to be providing the head of the linked list, CP head here. And obviously the syntax is off a little bit because I have to name the structure before I specify the rest here. So there we go. And this is also WFF node, WFF node, like so. All right. So now we have to chase all the way down to the end of the linked list. So the way to do this, we can do it recursively. We can also do it non-recursively. So I will go ahead and do this non-recursively, because when you have a long linked list and you do it recursively, that can chew up a lot of space on the stack unnecessarily, and we don't want this program to crash because we ran out of stack space. So we'll do it non-recursively, and in that case, it means while p head, whatever p head is pointing to, is not null, and we keep going by saying p next. Um, I'm just thinking here. Okay, we don't want to do it this way. All right. Because once we chase it down to the point, then we want to change the last one, but I don't want to change. Let's see. That'll work. That will work. Okay. So what we'll do is p head itself is a pointer to a structure. So we're going to change the next of that thing. No, that won't work. That will not work. So we need to change whatever p head is pointing to, which is a pointer to a struct WFF node. We change that to the pointer to the node that we are passed with, like this one. And then, oh, I take it back. Sorry. This is what we do when we get out of the loop, because this is after we have found the end of the entire linked list. And over here, we have not found the end of the list, so we have to chase down the whole thing. So basically, p head becomes the address of whatever p head is currently pointing to, which is a pointer to a struct node, and it is not null, so it is actually pointing to a valid structure. Then within that structure, we have a next member. So we are just basically chasing down the next pointer um, until we get to the end, which is a null, and then at that point we change whatever p head is pointing to the pointer that we want, so that therefore changing the end of the linked list. And then there's one more thing to do, because your PWN next also needs to be changed to a null, and this is how we terminate the entire linked list. Okay, so I think this is going to work. And then we just need a few helper things, to kind of confirm that we have no problem reading and actually creating the linked list. So then we need something to do the printing of um, a WFF. So that would be a WFF, print statement. Let's see. I'm, just thinking, do I want to print it to a string, or do I want to just, output the entire thing out to standard output? I'm just thinking. Um, we'll go ahead and we'll just print the entire thing to standard out, okay? Because it's easy enough to change it to, put it into a string. This is one of the things where, if you do this in C or C++, it is kind of a pain, because a string is not elastic in C or C++, meaning that, you have to pre-allocate a certain size unless you use a vector, which brings in a lot of unnecessary code. Um, in other type of programming languages like JavaScript or Python or something like that, strings are elastic arrays, which means you can always append to the end of an array without having to worry about how much space was originally allocated. So yeah, so this is going to be a little bit of a pain, but that's okay. So we'll say print WFF, and we'll be given a WFF. So we have WFF. This is, a pointer to a WFF. So what we'll do here, we know it is an array, so we need a local variable integer, so unsigned I as an index. And then what we'll do, I mean, there are a few ways to do this. I'm gonna do this, in the most general way. So we have a printf, well, in this case, I don't really need to use printf, but it's just a force of habit here. Okay, so I'm just beginning and ending the parentheses, and then we'll go ahead and go through the array and print each one out individually. So we have for I equals to 0, I is less than num var, and then plus I. And then we'll say, let's find out whether the corresponding variable to this position, position 0 is P, position 1 is Q, and so on. So we'll see whether that is a 1, a 0, or a -1, and then we'll choose what we want to do. So the first thing, there are many ways to structure this conditional statement, but the way I will do this is to say, if the WFF that PW is pointing to, and locating at index I if it is non-zero. So you can do this, to compare to non-zero, but this will also do. So I'm going to add this part here just so that it is clear that we are comparing it to non-zero. Okay, there we go. Because if it is 0, that means the variable is not mentioned in this particular WFF, and therefore there's nothing to print. So now we can now, oh, you know what? A switch statement would actually work even better. So we'll go ahead and change this to a switch statement. This is one of those really rare occasions where a switch statement actually makes slightly more sense than a conditional statement. I still don't like, how C and C++, handle a switch statement, because, for each case, you have to remember to use a break. But in this case, not breaking and letting it fall through actually makes sense. I'll show you why. Why I say that. So in case you have a negative one here, then we print the negation symbol, which is just an exclamation point, and then we fall through. We intentionally let it fall through to case one, where we will print the actual character corresponding to that position. So it is a percent %C, which means it is just a character. But the way we compute the character is to look at first var, and then we add the value p asterisk pw bracket I. So what we're doing here, oh, okay, I take it back. Not just I. So because when I is 0, first var plus I is just the character p itself, which is exactly what the character we want to print. When I is 1, we're going to print Q, and so on and so forth. So this is a very, very special occasion where a switch statement actually makes sense. Because not to do it using a switch statement, using conditional statements, it's going to make the code a little bit longer. It's not too bad. I mean, this break is really not necessary, but I'm going to put it here anyway. So anyway, that is how we print a single WFF. So I think we got some code here that we are almost ready to test it. Okay. And before we do that, I'm just going to go through the compile again to spot really kind of obvious mistakes on line 27. We have, is that a semicolon? What is it complaining about? Okay, I forgot to read the error message. All right. Yep. So it's a colon. I put in a colon when it's supposed to be a semicolon. That's why. All right. So we need something else to help us, traverse the linked list. So now we have append, and then we just need traverse linked list, and also to print it at the same time. So we'll also, in this case, pass the head of the entire linked list. So p head here. And then the traversal code is basically the same thing that we had earlier. So if p head does not, if whatever p head points to does not equal to 0, then we'll do this part here. Except this time we are not, okay, we need this line, okay, which allows us to move forward. But we also want to print before we move forward, what WFF is pointed to by the pointer that p head itself is pointing to. Whew, okay, so that means this is a pointer to a structure that has a member of WFF, and I think the member is just called W. It's on line 68 here. So this is what we want to print, and we need to take the address of this thing before we call the subroutine. So I cannot remember the name of the subroutine already, so let's go back and check that. It's called print WFF. Yeah, that kind of makes sense. Alright, so getting back to traverse, we will say print WFF, and that is what we want to print. And we have to pass the address of the member, and this is not right. I need an extra pair of parentheses right here. Okay, so we need to pass the address of the member of the structure that the pointer that is pointed to by p head to print WFF, because that's where the actual WFF is located. So anyway, this allows us to kind of scan, the input, and then we can construct the linked list, and then we can print it back out and see whether we got the same thing. So this is the minimum program that we need to write in order to check out whether the program is working or not. All right, so now we have a struct WFF node, and this is going to be the linked list. So we have the linked list starting with a null. And technically, to use camel casing, it has to be LL like that, because the second L is supposed to be capitalized. Um, this is the head of the linked list, and it is initialized to 0. Oh, we need something to allocate for a new structure. Okay, so I'm just thinking, what do I want to do here? Well, I suppose we can just make a new one here. Um, void read WFF. And since we're also creating a WFF node here, that's what we'll do here. And we'll make this return a pointer to a struct WFF node, like so. And I need to, okay, so I need to also pound include standard library, because now I need to do the malloc memory allocation, which is the same thing as new, and also free, which is the same thing as delete in C++. Okay, so right, so we are here. Um, okay, so we have struct WFF node pointing to result. Result equals to malloc. And with malloc, you have to do typecasting because it returns a void pointer, so we have to cast it back to a struct WFF node pointer. And then what we need to allocate, is we have to specify how many bytes to allocate. So that would be the size of a struct WFF node, like so. And then we also want to read that particular thing. All right, so now I need to think, because um, the code to actually do the reading is all the way up here, and it is expecting a space to put that stuff already, and also a string pointing to some kind of an input string. So if I want to do it this way, then it means this does gets a little bit it gets a little bit ugly. I'm just thinking, what I should do here. I think it is okay just to do it like this. Okay, so basically we're just allocating um, a new a new node, and return result here. All right, so when we get the result back, then we have to do the reading, using the W member, and then we can attach it to the end of the linked list. Okay, and since I do not want to access the member directly, then I can use something like this. Okay, WFF, star WFF node. Okay, wait, WFF node node get W. Okay, there we go. So that makes more sense. And we have struct WFF node P node, and we are just returning the address of P node points to W. All right. Okay, so now that we have all of these things, we can now test the program. All right, so we have uh, all right, so we have const char because I need to remember, at where are we at in terms of parsing the input. So we'll have, I'll just call it PDR, and initialize it to argv1, which is the second member of the array that represents the what is on the command line. And then we can say as long as, oof, okay, so hmm, because we will do the parsing first, and then, all right, so we have to first allocate for the array, for the WFF, and then we read into the W member of the node. So a do while loop would make more sense here because we otherwise there's no place to store the WFF. All right, so we'll do a do while here, and I don't know how to specify the condition to stay in the loop. Not yet, but that's okay. We'll get to it, eventually. So the first thing we need to do is to say WFF node star node p node, and we'll just go ahead and allocate for one. So this is a misnomer. We should not call it read. We'll just say allocate. All right, there we go. All right, so allocate a WFF node. Okay, there we go. And then this is when we read it. So when we read it, we have to update PTR using the result of read WFF. The first parameter to that thing is the address of the W member, and I just wrote a function to do that, but I cannot remember the name of that thing anymore. So what is it? That's just allocating, and right, there we go. Node get W. Okay, so I'm gonna split the screen so this way I can look at part of the program on one side and then while I'm programming the other side. All right, so there you go. It is, so we have to node get W p node, and it is the same name here. Alright, so the first parameter to read WFF is returning the address of member W of the node that p node is pointing to, and then the second parameter is going to be the string, and I want to be sure that this is how we wrote the subroutine, and that is correct. So it is using the string as the second parameter. Alright, so this is going to read it, and we'll say if PTR does not equal to 0, because when PTR equals to 0, that means we did not parse correctly. Then we'll go ahead and attach this to the end of the linked list. So I believe we have, oh, I forgot to do one thing. I forgot to initialize the linked list first. So we'll say init w, oh, okay, that's not the subroutine because I got one to initialize the linked list, which is init ll. And in this case, ll should be both uppercase because each one is representing a linked list. One is link, the other one is list. So we have init ll and the address of il. Okay. So with this, I don't need to do the initialization here because they're really doing the same thing. That is correct. Yep. Okay. I'm just double checking, and then from here we are going to append. So we call it append ll. Okay, once again, it should be both uppercase, so we'll change that. And then the parameter that we need to pass, the first one is the node that we just allocated, which is called p node here, which is a pointer to the node that we have just allocated and initialized by this time. And then the second one is going to be the linked list itself. So it's just LL, which is the linked list, and we need to pass the address of the linked list because it can potentially change it. Well, it'll only change it when the linked list was empty, because once it has one element, it will just kind of chase down the element, chase down to the last element and change only the next member of the very last element. All right, so when we terminate, that means your PTR has to be a null. So as long as PTR is non-null, we should continue like that. All right, so that looks good, and we have an else here, which means what if we attempted to read something and it is not something that's valid. So technically speaking, what we need to do is to free the memory that we just allocated. So that means p node should be deallocated in this case, because otherwise we have wasted one space. So this will do all the reading, and now we just need to print out everything that we have read as a test. So we just need to go to traverse. I think that's the routine is called traverse. So we go to traverse LL and give it the linked list, or the address of the linked list, like so. And I think we're good to go. All right, so we'll go ahead and compile the program. And obviously, I got some stuff here that needed to be fixed. On line 115, IL is undeclared. Okay. All right, so it's LL, not IL. Okay, there we go. And what else? 119 is using read WFF. Implicit declaration of function read WFF. So I was using the wrong name. All right, so we do not have a function called read WFF. I cannot remember what I init WFF. Okay, there we go. So we'll change read to init. It's more like parse, so I'm going to change the name to parse. There we go, parse. There we go, and then we go back to init WFF and change this to parse WFF. All right, so let's try to compile again. All right, so we got traverse LL. The second L should be in uppercase on line 130. Okay, there we go. And if you read the error message carefully, it actually reported. Um, it has a suggestion of, oh, maybe you meant the variable that has the second L being capitalized. All right, so now we just have traverse left, and it is just a matter of using the wrong name. So I forgot to change this one to uppercase L, and now it should be okay. Yep, there we go. So now we can compile with an executable, like so, and then we run the program, and we'll just give it like a very simple one to begin with, like just p init, and press the enter key. Syntax error near expected token p. That is because I might need to use double quotes to escape the entire thing. Alright, so this is an error message that's coming from the program itself. It is printing expecting open paren because it has reached the end. But you can also see how it printed the expression correctly. So the program seems to be working, at least do it with one single WFF in the CNF. So what we're gonna do is change the error message here, because we really don't need it to print the error message. Because if this is indeed the last one, then we just have to go back and say, okay, oh, okay, I know what to do, because we can print the error message here if p next is not a null character. In other words, we saw um, a non-null character, but it is also something that we are not expecting because a null character is fine. It is the terminator of a C string, so we will only print this error message when that happens. All right, so there are a few refinements, even at this point, because I need to print the end of line. That makes it look a little nicer. And I'm just thinking, do we have anything else to do here? I think we are good. So we are going to compile the program again and then do resolve. And this time we have P or Q. And then let's do a not S or not T. Um, oh, right. I need to quote everything. Um, the problem with not quoting is parentheses actually mean something in Bash, which is the shell script language that Linux uses. Um, Alright, so it still doesn't like that. Hmm. That's because exclamation point also has a special meaning. Oh, okay. I'm not sure whether single quote can fix this problem because I cannot remember whether single quote will change the interpretation of special symbols. Nope. Okay, so single quotes work. Alright, so now we have a program that can read WFFs in, do the parsing correctly, read the linked list, be able to traverse and print out the linked list, and so on. Alright, so next, okay, so we are going to do more stuff with WFFs. The first thing I need to do is to determine whether two WFFs can resolve or not based on a particular variable. So what we'll do is, right, um, is resolvable, okay, and it is going to have two WFFs, the pointers to two of them. So this is one, and this is the other one. And then what we need to do is, there's one more. Okay, we need one more thing. And which variable are we considering to do the resolving? And let me think. Hmm. Because in the process of trying to figure out whether it is resolvable, we can do the actual resolving already. So, um, okay, that's one more thing we also need to do is to see if two WFFs are the same. So we'll just do a EQU WFF first. Um, WFF PW1, WFF PW2, and then we just need an unsigned I and also an int result. So the result is by default a true unless we find a reason not to say that. So there we go. And then what we'll do is we are just going through every single position and see whether the values of the WFFs, the two WFFs, are the same for every single position. So we have for I equals to 0, I is less than numVar plus I. And I know this is it can be simplified a little bit, but and optimized a little bit, but for now we are just going to do it in a very very simple way. So we have result equals to result and um, these positions of the two WFFs, the same position of the two WFFs being the same. So now we have PW1, um, right, um, bracket I equals to PW2 bracket I2. There we go. So it will get the job done. It's not optimal because once result becomes false, it will never become true again. So if we really want to optimize this, we can say result and that, because this way when result becomes false, it will just kind of not continue the loop anymore. So instead of using breaks and conditional statements, this is I think is a little bit cleaner. All right, so this is for checking whether two WFFs are the same or not. And then we also need another one to do the actual resolution. So we'll have it needs a return value to basically say, did we actually resolve to something? So it's going to be the return value of int. It returns a 0 if it is not resolvable or does not give us anything useful, and it is going to return a non-zero when we did resolve. So resolve, and in this case we need three WFFs. So we have PW1 as the original, PW2 as the other one that we are trying to resolve unsigned position, or var, that is identifying which variable are we trying to use as the bridge, where one side is -1, the other side is 1. And then we also need PW3, which is the result. So we'll just call this the result of the resolution. All right, so now we are going to, this is typical of me. I'm going to have a variable, to store the return value of the subroutine. So unless I see a reason to return true, let's just say the default is false. So this way, if I don't see a reason to return true, I can just leave the default value of result. All right, so what do we need to do? The first thing we need to do is to confirm that the position of var of both of the WFF1 and WFF2, one has to be a 1 and one has to be a -1. Okay, so let's go ahead and see what kind of conditional statement is appropriate for that. There are two ways to construct this conditional statement. So we're going to do something like this. All right, so here we have the conditional statement. The question is, what do we use to specify the conditional statement? The most straightforward way to do it is to specify blah blah or blah blah. And the first one is basically using PW1 bracket var. Oh, okay, I need to be careful with the parentheses because this one does need the parentheses around the reference of PW1. So we need this to be 1, and we need, oops, that to be -1, because we are looking for the first one to be asserted and the second one to be negated. And so this one is going to be almost exactly the same, except we switch which one is negated and which one is not negated. So now if one of these two conditions is met, then we do the concatenation. So the concatenation, and putting it into the p result thing, is done by another loop. So we have unsigned I, to control the index of the loop. So we say for I equals to 0, I is less than num var plus plus I. And then we also have to exclude the processing of the variable that is acting as a bridge. So we have to say, okay, we only got something to do when I does not equal to var, which is the position or the variable that we are trying to use as a bridge. And we have already confirmed that we can use it as a bridge because of the conditions on line 46 and line 47. So now we are going to specify what to do here. All right, so we got a few possible scenarios. If they're both zeros, then the result is going to be a zero. If one is a zero, the other one is not a zero, then we use the other one. If one is a one and one is a negative, if they're both negative ones, they're fine. If they're both ones, they're fine. So we'll check with that first. So we'll now say if PW1 bracket I equals to PW PW2. Yeah, the casing is killing me. There we go. Bracket I. If they are the same, then we put this, just pick one and put that value into the result. So we now say P result bracket I equals to just pick one of them. So we'll just pick the first one. There we go. All right, so if this is not true, um, then we want to check for the condition where one is a zero, and then we pick the one that is not a zero. Um, there's a trick to this because we can add the two, and if the sum is a zero, we really got nothing to do. Well, let me see. Because if one is a one, the other one is a negative one, then the entire thing is useless. On the other hand, if oh, this is yeah, this is going to be a little bit ugly code here. Hmm. All right. Okay. So this is what we can do. So we'll say else if. Okay. So we're going to look at the sum, and as long as the sum does not equal to zero, we have something to do. So in this case, we add up PW1 bracket I and PW2 bracket I. And if the sum of these two is non-zero, that means they're not both zeros, and it is not the case that one is a one, the other one is a negative one. So this is actually meaningful, and we are going to. Ooh, okay. So we have to actually initialize p result, or change p result I to the sum of that thing. Um, So now the question is, do you want it to be more optimal, or do you want copy and pasting code? Copy and pasting code in this case is, I guess, acceptable. So we'll go ahead and do that. Um, I'm just, specifying what to paste into here. So this is acceptable, even though it is non-optimal, it is still okay. All right. So the else here is corresponding to they are not the same, okay, and they don't add up to something that's not zero. So we are now left with the case where um, we really should not do any processing, because what we end up with here is one is a one, the other one is a negative one, and I don't even care which one is one and which one is negative one, because the resulting the result of this resolution is giving us a 1 within the entire thing, which means the entire disjunction is going to be a 1. It's going to be true. So that means we do not have a meaningful result in this case. So in this case, we have to specify result being 0, because now everything is shot. So that means that the way I initialize result to 0 is wrong, because I should have initialized it to 1, assuming everything is good, until I know that something is not good. All right. So, but that also means we also need an else case here, because the else is corresponding to the variable that we intend to be using as a bridge could not be used as a bridge, because the condition specified on line 46 and line 47 is false. So now we have to actively specify and go like, no, the resolution did not happen. All right, so now we can now use the same trick as before. We can specify result and like this. So the idea is as soon as result becomes false, we can get out because there's no way you can get back. It should not get back to a non-zero result because there's nothing here that assigns a 1 to result. All right, so I think that should do it for resolving. So we are pretty close to getting everything done, assuming this thing compiles. So let's double check and make sure it compiles first. And of course it does not. Yeah, casing issues on line 37, 46, on 40, 46 again, and on line 55 it is missing a 1, and on line 55 it is the I shift the key 1 and got the exclamation point. So all kind of minor issues, and we'll do it one by one. 37 and 46 first. So on line 37, the this one needs to be capitalized, and then on line 46, same issue, capitalized, capitalized, and capitalized, capitalized. All right, so let's compile again. Okay, line 55, um, just wrong name because I was using an exclamation point instead of a 1. There we go. All right, so now the program is compiling again, but this time I want to see whether it can resolve correctly. So I'm going to I'm just trying to think, should I work on the actual code to try to resolve it, or should I um, do something else? Okay, so I'm thinking, I'm processing, thinking. Um, okay, I think I know what I want to do. All right, so I'm going to put some comments here. Okay, print what we just parsed. Okay, um, and that's what this initial code is doing. Um, right, there we go. All right, so now we are going to find what can be resolved. So to do that, we need 2 pointers to traverse the entire thing because one needs to traverse the first um, disjunction, and then the other one traverses the rest of the linked list. So we need a double loop, um, and yep. So we'll set up a double loop first. To before we set up the double loop, we are going to require some local variables. So we're going to have a head for the first disjunction. So we can say pw1 struct, um, what was it? WFF node pw1, and this is just going to be at the head of the linked list. So we have um, the head of the linked list, and then we have WFF node. Well, okay, this is the outer loop. So let's do the outer loop first. So we have a for loop, and okay, so I'll do it the more traditional way to put all the initialization inside the parentheses. So pw1 equals to whatever the linked list is pointing to. So we have lowercase l and then uppercase L. And as long as, okay, so the terminating condition is when pw1 is not the last thing. So that means pw1's next should not be a null, or the next of the next is not null. So we'll say this is not null, and the next of the next is also not null. because the first one simply means there is a next one, which means it is not the last one, but we actually want to make sure that PW1 is not even the second to the last one. Well, let's see. The second to the last one. Yeah, so just we just need it not to be the last one. There we go. That should be fine. And then for each iteration, we want PW1 to advance to the next one. So PW1 gets PW1 points to next. And that's it. That's the outer loop. And then as for the inner loop, it's going to start with whatever is next to PW1. So now we have for, a local variable, struct WFF node PW2. And then very similarly, we initialize PW2 to, but in this case, it is going to be PW1 next. And this is why we need this to be a non-null, because now PW2 can be the last one. And then the terminating condition is PW2 cannot be a null, because if it is a null, that means we have hit the end of the linked list. And to advance to the next iteration, PW2 gets PW2 points to next. So this is how we can iterate through every single WFFs. So now I just want to double check and make sure the structure of the loop is set up correctly. So by the time we get here, I just want to print the WFFs. So let me split the screen again because I cannot remember the name of the, oops, split, there we go, the name of the subroutine that can print WFF. There we go, print WFF. Kind of obvious, isn't it? Alright, so we'll go ahead and, alright, so we'll say printf, try to resolve. And then we have print WFF, and it's going to be the W of the first one. So we have node get W of PW1, and then we have the second one, which is print. We can just do a space and space, and then we print WFF node get W of PW2, and then we'll say printf backslash n, to terminate the line. So what this is going to do is it is telling us which two disjunctions or which two WFFs are we trying to resolve. So it's really just a check before I continue with this code any further, because if this is not working, we have to debug it first. All right, so let's check it. Compile. Of course, there's an error. Incompatible types on line 185. Alright, so PW1 is a WFF node pointer, and IL or LL is a double pointer, I think. I could be wrong. Oh, it is just a pointer. So that means we don't have to dereference on that line. Okay, so we are just starting with the first one, and then we keep moving forward until we hit the end, and then the same over here. Not the same over here, because this one is just using PW1 next. Okay, alright, so we'll compile again, and this time when we test run it, we have to give it something that we can potentially resolve, because well, actually it doesn't matter, because we just want to see whether it can process out of this. So we have P or Q, R or S, and I don't know, P or T or something like that. Okay, so in this case it should say it attempts to resolve P, the first one with the second one, and the first one with the last one, and then the second one with the last one. So it should give us One, two, three. They should give us 3 attempts. Yep, there we go. Okay, the printing did not work correctly because I forgot to print the plus between the variables. Okay, so minor issue here, not too big of a deal. But other than that, it seems to work. So we'll go back and fix the printing because I forgot to print the plus sign in between. So that means when we have a loop here, after we print, I mean, there are a few ways to do this. I actually should say, if this is not the first one, then we'll just, print the plus sign here. And we know whether it's the first one or not because if it is the first one, then I would be 0. But it doesn't mean that we have printed anything yet. So that means I need to track whether I have printed something yet, and I need a flag for that. Okay, so we'll go ahead and use a this is a syntactical difference between C++ and C. I think in C++ you can put a declaration of a variable anywhere, but in C you can only put it at the beginning of a scope. So that's kind of a little bit of an issue. So we'll declare up here and we say, oh no, we cannot do it there. We have to do it here. We'll just say counter. Okay, we initialize that to 0. And then every time we print something, we just increment the counter. So now, when we are here, we can now say if counter is 0, it means we have not printed anything yet, and we should not print a plus sign. On the other hand, if CNT or counter is non-zero, that means we have printed something already, so we need a plus to connect to the next variable. So we'll say, I mean, there are there are lots of ways to do this. For those people who keep saying, but Tak, you really like ternary expressions, right? Yes. Okay, so we can use that. So if count is non-zero, then we print the plus sign. Otherwise, if print is 0, we print the empty string. I mean, that's one way to do it. There we go. And then we just have to recompile the code and test the previous test case. And um, that is definitely not what I intended because it's also printing the plus sign when when the variable is missing. In other words, when the value of the position corresponding to the variable is a 0, it's printing a plus sign too. Um, yeah, that's an easy problem to solve. Okay, so what we need to do is to put this statement to, ooh, this can be a little bit tricky because um, hmm, it's a little bit tricky because if it is a 0, then we don't want to print the plus sign. Um, all right, so there's a way to fix this. I know this is not the easiest looking code, but we can do that. So we can basically say if that and that. That should do it. Okay, so let me explain what we are doing here. So as long as we are not dealing with the very first printed variable, and we actually have something to print. This part here basically specifies that we do have something to print because it is a non-zero. Then we'll print the plus sign, and then it will print the actual thing later on. Alright, so I think that should do it. Compile, of course, P, it's PW with an uppercase. There we go. Alright, so we'll try that again. Test case. Alright, so, yep, so we got it. We got it. We'll also try the negation, and, that works too. Alright, so now we have a way to pair up things and do all that stuff. So now it is a matter of so now we need to try to resolve because and then if it does resolve, then we'll go ahead and see if it is a new expression because we don't want to um, we only want to continue the loop if we have found something new. So now we go back to the source code and so this test code is working. Okay, so I can comment out the entire thing. So one quick and easy way to comment out a section of code like this is to use pound if and pound end if because that can it's better than using comments because this thing can work over a section of comments too. All right, so now we also need to go through every single variable and see if we can resolve for each possible variable. So now we have another local variable. So we have unsigned I, and then we say for I equal to 0, I is less than num var plus I. So this is the third level loop. And right, okay, so there we go. All right, so now we basically is saying, okay, we have one disjunction, we have another disjunction, and then we are now going through every single possible variable to see if we can resolve using that particular variable. So this part can look a little bit clumsy because, okay, so I'm going to explain why that is the case. So struct WFF node, and this is a new node P new, and we're going to call the subroutine. Okay, I cannot remember the name of the subroutine already, so we have to go back and check that. Allocate WFF node. There we go. So we have allocate WFF node. Okay, so we are just creating a new node here so that we have the storage for what we need in order to store the result of the resolution. Um, right, so now we just have to check to see if we can indeed resolve. And obviously, I forgot about the name of that particular subroutine as well. So let's scan and find it. It's not parse. It is resolve. Okay, there we go. All right, so now we will try to resolve, and I will store the result or the attempt to resolve into a local variable. So we'll say, can resolve is the variable, and we'll just go ahead and initialize that with resolve, resolve CNF, or resolve without even CNF. Okay, there we go. Um, we need the pointer to the first one, so that is the address of P, oh, okay, PW1 points to W. I mean, yeah, I should have used the get node thing. All right, so I'm going to break my own rule, for now, just so that we can see whether the code works or not. So this is the address of member W of the first disjunction, and then we have to do the same thing with the second one. So PW2 points to W, and now we want to specify which variable, which is controlled by the local variable I. And now we specify a place to store the result, which is the address of P new points to W. There we go. So we are now checking to see if, oh, okay, it doesn't like it because I forgot the semicolon at the end of the line. All right, so if can resolve is a 1, that means we just got something, and then we have to check whether that something is something that we have seen before. If it returns a 0, that means we didn't see anything. We did. There's no. We could not resolve it, and as a result, we can deallocate p new and then move on to the next iteration. So we just have to check can resolve. Then we got stuff to do. So I'm just going to comment here and say check for duplicates. And if not, else, then we can just say did not work out, deallocate. Okay, so deallocating means we are just doing calling free with the pointer to the new node that it was allocated but never really uh, never used anywhere. Okay, so now we need to check for duplicates. I mean, normally I would write another subroutine, just so that the code doesn't look, this nested and ugly. But for now, I'm just gonna, you know, do it quick and dirty. There we go, quick and dirty. So we'll look for duplicates, and result is gonna need a initialized value, but I'm not really quite sure which one I want to use first, which is okay. And then we also need struct WFF node, because I need to keep track of which one of the entire super CNF, which disjunction of the entire super CNF am I comparing to the result of the resolution. So we'll start from the beginning, and this is going to be, oh, I don't know, we'll just call it P node, and it is initialized to LL, which is the beginning of the entire linked list. And then we'll just go ahead and say while, let's see, should I do a while or, so we want to say result is initialized to a 1. So the while loop is going to say as long as we have not seen a duplicate and we are not at the end of the linked list, which means the P node is non-null, then we got stuff to do. There we go. So what we have to do here is to specify and say result equals to result, and this one is not duplicating either. Okay, so we are basically saying whatever the WFF is for the node that P node is pointing to is not duplicating, is not the same as the result of the resolution, which is the W member of the node that P new is pointing to. Alright, so now we have to go back here because I cannot remember the name of the subroutine to check for duplicate WFS. Okay, EQU WFF. Alright, so this one returns a 1 if and only if they are the same. So now we have to use a negation because because we are looking for something that's different, not the same. So we want to do a negation, EQU WFF, and we specify the two parameters. The first WFF is, I mean, it doesn't matter which order we are doing this. So we'll just say the first one is whatever the result is. Okay, so we'll say this is the address of P new points to W, or the address of member W of the node that P new is pointing to. Okay. And then the second one is going to be the address of the W member of whatever P node is pointing to. There we go. All right. So I'm just checking the parentheses. They all seem to match up okay. So as long as they are not the same, we can proceed to the next one. So we'll say this is probably not necessary. Um, yeah, it's not necessary. Let's not do that. So we'll just say P node is P node next. There we go. In other words, we're just moving on to the next one. And when this loop exits, there are two reasons why it can exit. One is result becomes false, and the second one is P node becomes null. Um, if result is non-zero, it means everything is different and we can keep it. So in that case, so we say if result, which means we are finding a new WFF that is different from the rest. So now we want to append it to the end of the entire linked list. So we got a subroutine to do that already, and obviously I forgot the name of that subroutine. I think it's, let's see, I'm pretty sure append. There we go. All right, so if result is true, then we want to append this to the very end of the entire linked list. So we'll say append, oops, ll, append to the linked list. Um, the new node that we are adding is pointed to by p node. That's the new one, and the linked list or the address of the head of the linked list is that. All right, so that's good. And we also have to specify the else because the else basically means yeah we got a resolution, but the result of the resolution, the WFF as the result of the resolution, is duplicating something that we have seen already. So in that case, the first thing we need to do is to say, oh, whatever p node is pointing to is not needed anymore because we are not adding this to the super CNF. But we also got something else to do now because as we do this, um, we want to see if, let me think about this. So as we add more things to the end, mhm, oh, also when we resolve to null, just all zeros, we also want to flag it because that means we can exit. So that means I need another subroutine here to see if I got a false. So we will say, oh, this is the wrong place to do it. And this would be the best place to put it. Okay, so int is WFF is false. There we go. Give it a WFF. And then what we do is we just have to scan for every single position and make sure all the variables are zeros because a zero means it's missing. So if all the variables are missing, it means we have false. All right, so we have unsigned I. Result is, okay, we'll just say it is by default false. Okay, return result here. For I start from 0, I is less than num var plus plus I. And we also want to say, result and, because once result becomes false, we are not going to turn it back into true. So result is result and we want the PW bracket I to be 0. That's what we're looking for. And we'll use additional parentheses to make sure that the grouping of the operators is correct. All right, so this will check whether a WFF is false or not. So when we do append, then we run the test. So we are going to need a new variable, and this is why you don't want to write subroutines that are too long because the nesting itself is going to be a killer. But I can sort of track this, okay, so I can still do this. All right, so this is the beginning of the entire loop here, and what we want to do is to use a local variable to remember whether we have already get to the false, okay? So we want to say CNF is false, is initialized to false because we want to be able to confirm that. So now every single level of loop here can say, well, if we cannot confirm the entire CNF is false, then we got work to do. So that's why we are adding the checking of this local variable at every single level. This way we can basically shortcut the whole thing. Um, if as soon as we find that the CNF itself is false. Okay, so a note here is most people would use breaks, a break statement to break out, or worse yet, go-tos. And instead of doing that, I am using a Boolean, basically is a Boolean variable, to indicate whether it is time to break out or not. So I think this is a better solution, but some people can certainly disagree. This is more of a programming style kind of question. So, all right, so now we can go to here and say CNF is false, is the result of WFF is false, and we just have to give it the P node points to W, because we have to pass the address of a WFF to the subroutine, so that's what we are passing. All right, so let me see. I think that should be it. Okay, so at the very end, okay, so this is also one reason why you don't want to write a program that looks like this, because look at all of these close braces here. I mean, it's difficult to match which one is which one. Fortunately, the editor that I'm using can basically go to the matching end of a brace, which is really handy in this case. So what we are doing here is we are matching the end here. So by this time, we have exited the outermost for loop, which means the looping is all done. So by this time, we want to see if the CNF is false, because if it is, that means the proposed theorem is indeed a theorem. If not, then we have hit a dead end. We cannot make new um, resolutions anymore. So we'll say here if CNF is false, then we have good news. Otherwise, it's like, okay, not great, but it is what it is. Okay, so over here we say printf contradiction. We'll just say contradiction here, and we'll say um, resolution dead end, not revolution dead end, just resolution dead end. There we go. All right, so we have a conclusion at least. So I think this should do it. Well, I mean, I'm not even sure whether it compiles or not. We'll find out. All right, of course it does not, because numvar is supposed to be all uppercase. You can see how the compiler is actually pretty smart now. It can match the name that it could not match or find, to things that are defined. Even though this is a macro definition, it's actually smart enough to find that it's like, maybe you meant this. All right, it's on line 15, and we just have to, oh, okay, that to uppercase, that to uppercase, and result is also supposed to be a integer, so we need to declare that. All right, so let's check that. All right, everything works okay, and now we give it this one, and this one is not resolvable, so it should come back and say it reaches the resolution dead end. Woohoo! All right, so let's make it resolvable. To make this one resolvable, we can let's see. So we can get to that. We can give it t. So if we give it t, we just have to give it not p as well. That should make it resolvable. Oh, segmentation fault. All right, so the program reaches a segmentation fault. Um, and now the question is, how do we fix this problem? So a segmentation fault is typically because we um, access a location that is not valid. So the best way to do it is to use a debugger. So I'm going to use a dash G, means this dash G here means we want to include the symbol table, which means we can now use the debugger. There we go. And when we use the debugger, we can specify the actual parameters like so. So we do a copy and a paste here, and then we run it. And even though we still have a segmentation fault, it gives us a little bit more clue as to where we are in the program when we get to the segmentation fault. So we got to a segmentation fault with append LL, and we can also see it is giving it's passing a null pointer as PWN, and certainly that is not going to work. And so we want to find out, who is calling whom, who's calling append LL. That is what BT is for, backtrace. So we are on line 229 in main, and that is the one calling append LL with a really bad argument of, the pointer is a null pointer. So we know which line to look at. The problem is not with append, the problem is with the function call of append in main, which is on line 229. Alright, so let's stop the debugger and go back and look at line 229. Okay, so it's this particular append here. No p node somehow is a 0 at this point, and of course it is going to be a 0. This is the wrong variable name to use. I would really meant to use pnew and not pnode, because pnode is only used to traverse to find a duplicate. So this is also, okay, as a lesson to myself, this also means I need better scope control, because pnode really does not need to exist past the end of concluding with a result. So that means it is better to put a local scope around this entire thing. So this way, a p node is not even visible past the end of this scope here. So it would not be possible for me to accidentally use it, like here. Well, let me try to compile this first so that you can actually see how the compiler can catch it now because it's out of scope. So that's basically what I meant earlier. So now we go to line 232 and basically say, no, we did not mean to use pnode, we meant to use pnew. Alright, so we compile again. Yeah, of course, I consistently used the wrong thing, and I forgot the line number is 236. There we go, 236. So free pnew. There we go. Alright, so we compiled, and we can run the previous test case now. There we go. Resolution dead end. Alright. So let me just do it mentally and see if yeah, it should resolve to a null. And it got to a dead end because I really should put the entire thing in a bigger loop. Okay, yeah. So the problem is, the new things that we append here, once we get past a certain point, those things would not get a chance to resolve with other things that we have, the other results of earlier resolution. In other words, this particular method does not necessarily um, resolve every disjunction with all of the other disjunctions because it's only doing a one pass thing. So every time we find a new um, item, we need to remember that so that we can repeat the outermost loop. So we need one more loop on top of the outermost loop. All right, so we go to this code. Oh, wait. Okay, so in order to test the program and debug it, I'm going to give it a really obvious case to make sure that it does recognize this is resolvable to a 0. Nope. Okay, so we have a problem of not being able to recognize, that we have a um, 0 in the end. So, all right. So the question is, how do we debug this one, right? So to debug this one, we got a few choices. We can print out the new WFF. This way we can just kind of print it out and use that for debugging purposes. So print WFS is what we need if we did find a new one. So we got a new one when we get to here. Yep. So this is when we confirmed that we got a new one. So now we can say print WFF um, the address of p new points to w. There we go. All right. So this way we can kind of confirm whether we actually got the false or not. Okay. So we GCC again. Um. Hmm. Oh, I forgot the semicolon on line 232. That's also coming from programming too much in JavaScript, because in JavaScript you don't really need an semicolon at the end. So GCC again, and then we go back and retest the trivial case, and it did. Okay, so this is telling us that it got to the empty disjunction. So not being able to detect that we got a false is the problem of the subroutine that is supposed to return true when everything is 0. So we know where the problem is, which is this one here. So it means this one is returning a false all the time. Okay, so let's check out what this is doing. So result is result end. Position I of the WFF equals to 0. That seems right to me. All right, CNS is false is getting the result of WFF is false. Well, we can also just do a printf CNF is false question mark found contradiction colon empty string, because I just need to know whether we found a contradiction on this line or not. And over here, so CNF is false is never true after this line. So we'll find out. Recompile first and then run it. So that means WFF is false, is not working correctly. So the proper way to do this is to use the debugger to do it. So let's actually do that. Let's use the debugger. So we'll use GDB resolve, and then we'll run it with the same argument that we used earlier, which is P and not P. Oh, I forgot to put a breakpoint first. So we put a breakpoint on WFF is false. So this means, when we get into the entry point, when we get to the entry point of WFF is false, it's going to pause execution. So now we can actually test it like so. And now we get to WFF is false. And now we can single step through the whole thing. So single step and result and oh, I think I might know why it is having a problem. Okay. And we can also, just print out whatever WPW is. So we have Oh, okay. So we do have something that is non-null. Um, so we'll take a look at what it is first. Um, right, there we go. So we have a really strange value. So that is telling me that resolve is not working correctly because this looks like it's basically uninitialized. Where p is is uninitialized, and this whole thing is the result of resolve. So the resolve subroutine is not functioning correctly. All right, so we'll go ahead and take a look at that. So we look up resolve. This is it. All right. So what this is telling us is p result is not getting a value sometimes when it is supposed to be getting a value. Right, because when okay, I know why it is. What's happening here? Because we only put a value into the result of the resolution for variables that are not being the breach variable. But we did not specify what to do with the breach variable. So we have to remember that for the breach variable, we have to put a zero there. So result bracket I should get a zero because the breach variable disappears. Meaning that in the first WFF, if there's a variable, and on the other one the same variable is negated, that variable disappears in the concatenation. I forgot to do that, and that's why the value corresponding to p is uninitialized because this loop here would initialize every single other position except for the breach variable, the one that is used to trigger the resolution. So that is why. Okay, so GCC again, and we'll just run it without the debugger. All right, so we found contradiction and contradiction. Yes, it's just a error message thing. So we'll say found the resolution. Oops, found contradiction. All right, so this one I want to keep. Oh no, actually, I take it back. This one I want to comment out because we are still deep in the loop here. I only put this one in, quote unquote, for debugging purposes, and we'll keep the other one. And we don't even need to print the new one out anymore, so we can comment that out. I mean, wait, hold on a second. I do want to print it out because that's the part of the answer, right? All right, so we'll go ahead and give it one of the earlier ones that is a little bit more complex, and like this one. And this one is it's working. I just forgot to compile first, and that's why it still has the found contradiction. So we'll do one more time, and um, other than formatting, this is now working correctly. All right, so now we can plug in um, the one from our example, that we used in class today. And I think that's resolve.txt. Yep. So this is let me find the super CNF. This is our super CNF here. So we'll go ahead and put this into the clipboard. There we go. And then we paste it here. Oops. Ah, okay. Keyboard error. I mean, operator error. There we go. All right. So this one has a resolution dead end. This one does not work. But that's this is what I mean. I can refine it so that it can actually indicate which position or which variable is used between which two disjunction and what ends up as the result of that. But this is, without any simplification. It does not use absorption, but it basically, it tells us, whether we get to the end or not. So the earlier question that I had of, whether we need to, whether this will miss certain things, the answer is probably no, because as we construct the new, as we perform resolution and we add more to the end, um, the outer loop is going to catch it. The outer loop, basically resets, when the inner loop hits the end. So the inner loop, would actually append more things to the end, but it would also, continue to process those. So if there is a resolution, then the resulting disjunction of the resolution would be representative of the two things that we used for the resolution. So I think, I have to double check, the math and the logic of this, but I think this does not require a second loop to do its job. So I'm gonna do this one. I'm gonna retry this, with the second theorem and see if it, gets to a resolution or get to the contradiction at the end. So anyway, I think the program is done, and if I do need to modify the program, I will post that as well. All right, so I'm not really sure how long this has been, because um, I don't think there's a counter. There's a timer here to show me the time. Anyway, I'm gonna post this. I know most of you are gonna ignore this entire thing, because it's just me talking about, how I write programs. I mean, who wants to watch that? So anyway, if you do watch this, thank you, because it's not a waste of my time. But I was interested in writing this program to begin with anyway, so it's not really a waste of my time anyway. So all right, I hope this helps some people in some way.